At this very moment, across the United States alone, thousands of commercial aircraft are hurtling through the sky at nearly 500 miles per hour, separated by what often amounts to less than 3 horizontal miles and just 1,000 vertical feet. And yet, they never touch. No collisions. No guessing games. But here's the thing most people get wrong. The system keeping all these planes apart isn't some hyper-advanced AI. It runs on old-school radar geometry, rigid protocols, and humans who've spent decades perfecting a very particular kind of choreography. What you probably imagine is a giant GPS screen, where a controller watches dots move and gives orders. That picture isn't false, it's just missing about 10 layers of complexity. The real system is a chain of separate control facilities, each one handling a specific slice of airspace, passing planes from link to link like relay racers. Miss even one handoff, and the entire safety margin shrinks dangerously. The chain starts before takeoff, when a flight plan gets filed electronically. Safety is a relay race, not a fortress. The Air Traffic Control System Command Center then analyzes nationwide traffic flow and sometimes decides, hours ahead, that your plane needs to wait at the gate. This is ground delay management. And the reason the sky looks clear outside your window? The congestion hasn't happened yet. It's being prevented invisibly. After pushback, 3 separate ground-based controllers take over: ground control, clearance delivery, and the local tower. The tower controller manages the visible airspace around the airport, typically just a few miles wide and a few thousand feet high. At major hubs like Chicago O'Hare, different controllers handle different runways during peak hours because cognitive load spikes fast. But here's the part that surprises people. Once the plane climbs beyond tower airspace, it doesn't go straight to a high-altitude radar center. It enters TRACON, Terminal Radar Approach Control. Think of a bubble tens of miles wide, reaching up to the mid-teens in altitude. Inside this bubble, controllers solve a brutal geometric puzzle, merging arrivals from multiple directions at different speeds onto a single final approach path. Imagine merging 4 lanes of highway traffic into one, but the cars are doing 250 knots, and the merge point is a single runway threshold. And the tools? Not magic. Secondary Surveillance Radar, or SURA, interrogates each plane's transponder. The transponder replies with a 4-digit squawk code and, on most modern aircraft, altitude data. That's how the screen shows not just a blip, but a full data tag: call sign, altitude, ground speed. Radar doesn't guess, it interrogates. Lose that transponder signal, and the plane becomes incredibly hard to track. That's why flying above 18,000 feet in the US without a working transponder is illegal. Above that altitude, aircraft enter Class A airspace and get handed to an Air Route Traffic Control Center, an ARTCC. There are 22 of these centers covering the lower 48 states. Each manages a massive block of high-altitude airspace. At cruise altitude, separation standards are 1,000 vertical feet between planes at different levels on the same route and 3 nautical miles horizontally, but only within. Radar coverage. Those numbers aren't random. They come from radar accuracy limits, aircraft performance, and the time a controller needs to issue an instruction and have a pilot execute it. Go tighter, and you're eating into a safety margin that exists for a reason. But what happens when surveillance gets better? That's the trade-off nobody mentions. More precise tracking allows tighter separation, which means more planes in the same airspace. That's exactly why the FAA is pushing ADS-B, Automatic Dependent Surveillance Broadcast. Instead of waiting for a radar sweep every few seconds, ADS-B-equipped aircraft broadcast their GPS position once per second. More frequent updates mean higher position confidence. That lets controllers draw safety boundaries tighter without reducing the actual margin. The real stress test? Oceanic airspace. No ground-based radar whatsoever. Over the North Atlantic, separation is procedural, not real-time. Planes file position reports every several minutes. Controllers at Shanwick and Gander oceanic centers manage hundreds of aircraft along tracks that shift daily based on the jet stream. There is no radar confirmation. The math has to be right before departure because there's no live correction available. And yet, it works. A reminder that radar coverage is a relatively recent geographically limited luxury. So what does the whole system add up to? Redundancy by design. Segmented by altitude and phase of flight. Built on the assumption that any single tool or controller can fail, the radar can lose a return, the radio can break, the controller can make a mistake. The layers exist so no single failure causes catastrophe. Separation standards aren't about flying that close on purpose, they're the minimum distance where a human working with real hardware and real communication delays can still. Reliably intervene. If you found this breakdown useful, hit like for more deep dives on exhaust zone. The next time your flight sits in a holding pattern 20 miles from the runway, you're not seeing inefficiency. You're watching a system designed to absorb unpredictability, second by second, without ever letting two aircraft occupy the same piece of sky, doing it thousands of times a day. Every day, while almost no one notices,